Welcome to this explainer. If you are a student or researcher getting ready for a big defense or a major project pitch meeting, well, you are absolutely in the right place. Today, we're going to walk through exactly how to confidently pitch a highly advanced piece of software engineering to an academic panel. Specifically, we are breaking down the quality-aware multi-stage deep learning pipeline for peripheral blood cell detection and classification. It's a mouthful, I know, but we're going to visually map out your entire presentation so you can stand up there and explain this complex MLOps system with total clarity and authority. Okay, let's dive right in.
So here's our game plan to establish immediate credibility and give your panel a clear roadmap. We're covering 1, the clinical AI problem, 2, powering the AI with your datasets, 3, architecting the pipeline, 4, explaining the AI using GradCam, 5, the interactive prototype, and 6, your final impact. Let's get to it. Section 1, the clinical AI problem. Let's start things off by completely shattering the illusion of perfect data.
When you're pitching this, you absolutely have to start by contrasting how standard models behave. Sure, they show high accuracy on perfectly pre-curated datasets, but they fail spectacularly out in the real world. You see, automated computer vision tools in clinical hematology are incredibly sensitive. When an unmonitored end-to-end model encounters a degraded, real-world blood smear image, stuff with motion blur, lens defocus, artifact noise, or just messy cellular clumps, it doesn't just fail quietly, it generates high-confidence, totally incorrect diagnostic predictions. You need to make your panel understand that this lack of a structural verification layer is exactly what triggers massive downstream systemic errors.
And this brings us to a really critical moment in your pitch. You want to look at your panel and ask them this exact question. How do we stop corrupted inputs from triggering systemic errors? It's a brilliant way to illustrate the practical research gap. It perfectly sets up the absolute necessity for a structural validation guard, basically a low-overhead quality gateway that checks the image's integrity before any of those heavy, expensive inference computing tasks even start. Moving right along to Section 2, powering the AI with datasets. Your evaluators are going to want to know exactly what's under the hood, so lay it out clearly. You aren't just blindly throwing data at a single model here. You've got Resource A, the BCCD dataset, which has 364 complete digital blood smear fields. That is used specifically to train your Stage 1 YOLO V8 localization network to find white blood cells, red blood cells, and platelets. Then you step it up with Resource B, the canonical peripheral blood cell dataset. We're talking over 17,000 high-resolution, pathologist-verified single-cell images, used specifically for your Stage 2 CNN to handle fine-grained classification into 8 distinct morphology groups. Breaking it down like this proves you have a highly deliberate modular engineering approach. All right, Section 3, architecting the 3-stage pipeline. This right here is the technical heartbeat of your project. Walk your audience step by step through this decoupled architecture. Explain how incoming full-smear pixel arrays first hit Stage 0, your quality gateway. Emphasize how this gateway deliberately halts bad data, spitting back a rejection error before wasting any heavy inference computing power. If the image is good and passes, boom, it moves to Stage 1, the YOLO V8 localization core. That runs anchor-free bounding box regression to extract individual cells. Finally, those cropped regions of interest pass to Stage 2, where a pre-trained ResNet or EfficientNet model handles the deep single-cell morphological categorization. Now, to really blow the panel away, break down that Stage 0 gateway. You can actually explain this like a bouncer at an exclusive club checking IDs. You've got 3 algorithmic filters checking the ID of the image. First up, the sharpness audit module calculates a modified Laplacian variance score. If it's too low, the image gets bounced for motion blur. Next, the exposure filter checks the global color histogram variance to catch overexposed or poorly stained slides. And third, the clump overlap filter, which is a shallow, low-overhead binary CNN, stops the whole process if the blood smear field is just too overcrowded. It is a wildly robust, multi-tiered defense system. Okay, on to Section 4, explaining the AI with GradCam. Because let's face it, modern medical AI demands trust. You need to show them your model isn't just randomly guessing, so define GradCam clearly. GradCam, or gradient-weighted class activation mapping, is your Stage 3 post-hoc visual explainability layer. Tell the panel exactly how it works. Your pipeline feeds the classification score back through the network layers to calculate gradients relative to that final convolutional layer. This creates a visual heat map right over the cell image. It brilliantly proves to the user exactly which structural cell patterns drove the model's final classification. It literally opens up the black box.
Next up, Section 5, the interactive prototype. Academic panels love theory, but they absolutely lose their minds over functioning full-stack software.
You really want to highlight your modern tech stack here to prove full-stack engineering feasibility. You didn't just write a basic Python script, you built a real, tangible system. Point out that your backend architecture relies on fast API and Python for low-latency, asynchronous routing of those heavy image arrays and model weights, and then explain how that's perfectly paired with a snappy, responsive client interface built on Streamlit or React.
Walk the evaluators through the exact user experience to show total operational transparency. Imagine a user drags and drops an image into the upload portal. Instantly, the Gatekeeper Alert module throws up either a green validation checkmark or a red error warning asking for a re-upload if the quality gate gets triggered. If it gets the green light, the visual canvas dynamically draws bounding box outlines over the localized cells, and your XAI Diagnostics module pops up that GradCam heat map right next to the final class prediction. It's seamless.
Finally, we arrive at Section 6, pitching the final impact. You've shown them the problem, the data, the architecture, and the software. Now you bring it all home.
Before the big reveal, you've got to set your system boundaries. This is crucial because it reassures the panel that you know the difference between an educational research tool and an actual clinical doctor. Be crystal clear. Your framework is a research prototype without clinical human diagnostic certification. It gives statistical estimates that still require independent medical validation. Also, lean into the fact that you maintain strict ethical compliance by drawing exclusively from pre-anonymized public datasets. That means absolutely zero exposure to personally identifiable information or PII. Now, for the absolute proof, you have to show that your pipeline actually stops downstream errors compared to a standard baseline model. Break down your controlled experiment where you hit test images with artificial Gaussian blur, motion distortion, and illumination attenuation. Explain that a baseline system with no quality gate sees a massive drop in accuracy, spits out high false diagnoses, and has a 0% rejection rate. It just blindly accepts garbage. Contrast that disaster with your proposed system with the stage 0 gate active. It maintains high classification accuracy, it drops false alarms to near 0%, and it actually performs safe automated software rejection. It works exactly like it's supposed to.
And you close out with this incredibly provocative thought. Look right at your panel and ask them, as AI enters critical clinical workflows, shouldn't structural validation guards become the universal standard for trustworthy software? Ending on a forward-thinking question like that doesn't just summarize why your pipeline is necessary. It leaves your evaluators seriously impressed, thinking deeply about the future of trustworthy medical AI, and more than ready to give your project the amazing marks it deserves.